announcements. We have a quiz today. Hopefully everybody remembered that. You had a homework assignment that was due yesterday. So if you haven't done that, you're going to want to get on top of that. You have a vocabulary assignment that is due tomorrow for chapter 12. That's Kinetics, the next chapter we're getting into. And then I was left some flyers. So if you're interested in veterinary medicine, the college pre-vet club is meeting tomorrow. They will be in 112, which is the big room downstairs in the lobby area at 7 p.m. They are going to have Dr. Antu Radhakrishnan, who is a vet and internal medicine specialist at Bluegrass Veterinary Specialist and Animal Emergency Clinic in Lexington. And he's going to be speaking about his experiences in vet school and his residency and his specialty in internal medicine. And apparently you can attend either in person or online via Zoom. So I'm not sure how you get the Zoom link. It does not indicate that. So there you go. And then, as you probably know, Pi Day is usually March the 14th because 3.14. But that usually falls over our spring break. And so the NPC club isn't used to being able to do Pi Day on Pi Day, and they kind of got behind the game. And so they're doing their Pi Day thing this Wednesday, the 23rd, and that will be also in the lobby area, not in 112, but in the lobby area. Wednesday, I think it's at 6 p.m. and there'll be pie, obviously, and pie trivia. So sounds like a good time. Anything involving food. So those are some options for you. Any questions about those things? Yeah. It's due Thursday. Okay, let's call it Thursday. Yeah. Okay, I can change the due date on that and it'll remove the grade penalty for you. Thank you for letting me know. All right. And if you don't see that change before class on Wednesday, send me an email because sometimes when I leave the room, I forget. So. Okay. I had a couple of questions about some Chem 101 homework. So I'm going to do those over here on my notebook. Okay, so we have a question here. This isn't showing all of it. Okay. A solution of toluene in 301 grams of cyclohexane has a boiling point of 98.3. How many moles of toluene are in the solution? And then it asks for, or it gives you the information about the KB and the TB. So, this question is going to rely on using the boiling point to figure out molality. Now I've got to go back to my dumb. Okay, so we had is C7H8, and then we have cyclohexane. We have 301 grams, which is equal to 0.301 kilograms. And we have TB original is 90.30. Mix. Oh, sorry. 90.30. The original is 80.9. And KB is 2.92. Okay. So since we're given the boiling point of both the mixture and the pure thing, we are probably going to need to use the boiling point change equation. Delta TB is equal to IMAB. And these are compounds that involve only carbon and oxygen, or carbon and hydrogen, so no metals. So I is going to be equal to 1. All right. And then we don't know the molality, but we can find change in TB. So that's going to be 9 point something, 4, I think. 0.3 minus 8.9, 9.4 degrees. We don't know M, and then KB is 2.92. Okay, so we have all of that except for M. Remember, M at this point is molality, not moles. But we're going to rearrange to solve for that. So we're going to have 9.40 degrees Celsius divided by 2.92 degrees Celsius per molal. And I'm just going to let that one disappear because, you know, ones don't do too much multiplication. This gives us a molality of 3.22 moles per kilogram, but we have the kilogram of our solvent, so moles will be equal to 3.22 moles per kilogram times 0.301 kilograms. And that's going to give us 0.969 moles. And that's the color.
For I, will it always be 1 or less?
So I is our factor that tells us how many particles it breaks into. So if I only have nonmetals, it's 1. But if I have an ionic compound, it depends on how many ions there are. And your very first question on your quiz is, what is the value of I for these different substances? So you look at the formula, and if it's ionic, it's how many things it breaks up into. And if it's covalent, then it's just 1. All right, any other questions? Yeah.
Am I doing 11 as well?
11. All right, so the freezing point of pure benzene is EF is equal to 5.49 degrees Celsius. The mixture is of the solution is negative 13.0. AF is 5.12. We should maybe find exactly what is the molality of the part. All right, so this one's actually even a little bit simpler. We just have to stop at the molality. Okay, so we've got all of this freezing point. We've got all of this freezing point information, so we're probably going to use delta TF is equal to negative IMAF. So the delta TF is the difference between these two. So tricky thing here is this negative 13 isn't the change. That's the final endpoint. So you have to subtract these two. So 5.49 minus a negative 13 is 18.49. I is 1 again because toluene and benzene are both organic compounds. M is what we're looking for, and then KF was 5.12. So this one's just rearranging the equation and solving for that value. Oh, and since this went down, this is negative. So I should have the negative 13 minus the 5. Okay, so our negatives cancel out. And we have molality is 3.61 moles per liter. All right. Okay, so wanted to do a couple of things before your quiz. The first thing was to go back and look a little bit at entropy and enthalpy and the relationship between them. We talked about entropy a little bit at the beginning of the chapter, but really didn't clarify what that relationship was. We're going to look at that in a little bit more detail here. So, this is how we get the graph. All right, so entropy and enthalpy sound similar, different things, but these are driving forces for a reaction. Driving forces tell us, is this reaction going to go? What is favored? Enthalpy, we use the letter H. Talked about that last fall. We call that heat sometimes. Entropy, we use the letter S. And that's a measure of disorder. So we also said that the universe likes it when things get more disordered because organizing things takes energy. So it's just easier to let them get disordered on their own. So when entropy is positive, that's favored. Enthalpy, on the other hand, it is favored when we release energy to the environment because as we release that heat, the products go down in energy and lower energy for our chemicals is more stable. Okay. So negative enthalpy changes are favored. So these two things are kind of going in opposite directions. So the way that we put these together is with something called Gibbs free energy. So Gibbs free energy combines the enthalpy, the entropy, and temperature to tell us whether or not a reaction is going to go. Okay. So if the change in delta G, or the change in G, which is delta G, is positive, we say that is non-spontaneous. That's not going to happen. So this says won't happen if you can't read my sloppy handwriting. Right, so at room temperature, if I'm trying to freeze ice or freeze water into ice, it's just never going to happen. Okay. If delta G is less than 0, then it is spontaneous. That's a reaction that will go. Now we'll talk about in the next chapter how sometimes it needs a little bit of a nudge called an activation energy to get started. But once it gets started, it's ready to go. So this would be like striking a match. You get that match started and it's just going to go to town and burn. And then if we're right at 0, this is a state we call equilibrium. We've talked about that a little bit with our phase changes and a little bit with solubility. This is when we have both the forward and the forward and backwards happening at the same time. So for a phase change, we're both evaporating and condensing, or we're both freezing and melting at the same time. For solubility, we are both dissolving some of the salts that might be around, but we're also precipitating things at the same time, and they're happening at the same rate. So I'm not really changing anything. but I have both things going on at the same time. So this is our formula that mathematically puts everything together, that if we have numbers, we can plug it into. And we're not going to worry so much about the numbers right now. We're just going to kind of look at positives and negatives. But as you go on in chemistry, you may end up seeing this if you go on. Some of you will not. And so you may see this formula. But in looking at this formula, we can see we've got delta H minus ST. So it's going to depend on whether this is positive or this is positive or this is negative or this is negative as to whether or not this reaction is going to go. And is that a question or a stretch?
No.
Okay. All right. So let's say if I have delta H is negative and delta S is positive. So I've got a negative under here and I've got a positive under here, but I'm subtracting off that positive. So I've got a negative minus something. Then what's going to end up happening? I have to have a negative result, right? Okay, so delta G would be negative, and that would be a spontaneous reaction. Okay? And that's the case with lighting a match. So I've got my chemicals organized into the wood and into the phosphorus is actually crystalline. That's highly ordered. When I strike the match, they end up going into carbon dioxide and water. We know gases end up being much less ordered than solids. So we got a big increase in our entropy, but we're also releasing heat and light. So we've got a negative here. Okay, so this is a spontaneous reaction. All right, so in the opposite case, if I have delta H is positive and delta S is negative, then this positive is something that's not favored, the negative is something that's not favored, and I'm probably not going to have the reaction go. All right, so if I am cooling, or if I am freezing something, I know this was not really intuitive, but when I freeze something, it releases heat to the environment. So that's positive here. And then if I increase the order, I decrease the disorder. So freezing something is making crystals. So this is negative. So a positive minus a negative, this is also going to be positive, is going to give us a positive result. Okay. So that gives us two sort of zones to think about. So this graph that I have here, if you think of this as like an XY axis, so this is the X axis here, but instead of X, I'm calling it delta S. And this is the Y axis, but instead of Y, I'm calling it delta H. Then when I'm in the region where I have delta S is positive, but I'm below the line for delta H, that's negative, that's my spontaneous region. So delta H is negative, delta S is positive, that's spontaneous. And spontaneous means what? It's going to go or not go. Spontaneous is it's going to go. Okay. If delta S is negative, this is getting more order over here, and delta H is positive, I'm putting energy in, then this is a non-spontaneous region. It's not going to go. But I'm going to have all kinds of scenarios where I have both are positive or both are negative. And if that's the case, it's going to depend on the temperature. Okay, so those are going to be, which one's bigger? The amount that applies to the enthalpy or the amount that applies to the entropy. But since our equation here has entropy times T, the temperature is going to be a factor. Now, something we should say is this T is in Kelvin. Okay. And can Kelvin be negative? Kelvin is always positive, so that's not going to change the sign of it. All right. So let's say we are dissolving a gas. A gas is very disordered. When we dissolve it, we put it into a smaller container and organize it more. Okay. And so our delta S is negative. Okay. So that means I have some delta H minus a negative. Well, minus a negative is adding. So I'm adding over here. So what does delta H have to be in order to make delta G negative? If this part is positive, and I want this to be negative, what does this have to be? It has to be negative, right? So I have to have delta H plus something be negative. So for gas to dissolve, delta H must be negative. And it can't just be a little bit negative. It has to be sufficiently negative that it counteracts all of that S delta T or delta ST thing. And so this can tell us something about whether the gas is going to dissolve better at high temperatures or low temperatures. Because we can look at how the size of T is going to affect the size of this part of the equation. We said it's temperature dependent, but we want the impact of delta H to be greater, right? We need delta H to be negative, but we need it to be a lot more negative, okay? So do we want T to be big or small? Small, so that whatever impact the S has, it's a small impact. And so if that's small, that means a low temperature, gases dissolve better at lower temperatures. So if you buy a soda and you're not going to drink it right away, you don't put it in a cupboard, you put it in a refrigerator. You certainly don't put it in like a garage or something where it might get warm over the summer. You keep it someplace cold, and part of the reason for that is so that you keep that carbon dioxide dissolved in. So one of the questions on your exam had to do with an energy diagram, and it involved mixing things, and you ended up right back where you started. So it wasn't really exothermic or endothermic as far as delta H was concerned. So if delta G equals delta H minus S, delta ST, if this is 0, what has to happen to delta S? Does it need to be positive or negative? It needs to be positive so that this can be negative. And so that was one that we hadn't really gone into this before the exam. So that's why the correct answer was this thing about entropy that you're like, entropy is not even on this graph. And that's why I didn't have that question. All right. I was going to get into, I have a minute. I'm going to get into just a little bit of the introduction of chapter 12, and then we'll take our quiz. All right, so chapter 12 is about kinetics. And kinetics has to do with the speed of a reaction. So we have a lot of spontaneous reactions that go on here. Spontaneous, meaning that it's definitely going to occur. But they go at different rates. So an explosion is going to happen over a few seconds. If I have fruit ripening and then potentially rotting, a few days to a few weeks. If I have nails that are rusting, that might take me a year or two, depending on how rusty you want it to be before you call it rusted. the age from an infant to a grandmother or grandfather, or somebody is appropriate age for that, but not necessarily having kids, aging regardless, that is going to be over years, decades, okay? So these take different time frames. So kinetics is the study of, well, what makes a reaction go faster or slower? And then as human beings, we always want to manipulate things. We like to be in control. So how can we control how fast things are going? All right, so definition here. Kinetics is the study of the rates of chemical reactions. And so our example at the bottom here is just kind of showing balls of one color turning into balls of different color with a clock showing the time. And I'll talk about that in just a second. But the rates are going to depend on a few things. Okay? The two biggies that we will look at are temperature and concentration. And this is because in order for a reaction to go, molecules have to collide with one another. So the higher the temperature, the more often they collide with one another. And with high concentrations, there are more things to run into. So the more often they collide with one another. So it's all about increasing the number of collisions. But it also can depend on physical state. Now, we won't spend too much time on this. But if we think about a liquid or a gas, those molecules can mix together really well. So we can have lots of interactions with them. But if I have solids and I just put two solids together, they can only interact at the surface of the particles. The particles on the inside are just touching other particles of the same kind. So if I have a particle of aluminum, I might have millions of aluminum atoms and only the ones on the outside can actually do the reacting. And so that means whether it is a solid, liquid, or a gas matters, but it also depends on the surface area. Because if I had just a huge block of aluminum, that would be different than if I took that same amount of aluminum and scraped it into dust and that had smaller particles. All right, so we will answer the question of why on Wednesday.